Buenos dias, clase, and welcome back to FRQ number 3, the experimental design, aka my fave, because it's the easiest one to get partial credit on. So if you don't have the questions, they are linked in the description from the College Board website. We're going to do this in the actual test book, especially for this question because the graphing axes are a little bit different, so that you can see how yours stacked up. So we have a horizontal spring with a known spring constant K attached to a wall. A block of known mass M is placed on a horizontal surface next to but not attached to the spring. The spring is at its relaxed length when the block is at a position x equals 0, and there is friction between the block and the surface, but only for positions x greater than 0. We're asked to experimentally determine the coefficient of kinetic friction between the block and the surface using a graph. And we only have access to a meter stick. So since we only have access to a meter stick, that means we are only able to measure lengths, heights, distances, etc. So anytime you see a spring and then you're going to go slide on some surface or up a hill or something like that, it's going to be conservation of energy every time. 99% of the time. We're not going to say every time because then you'll find the one case and yeah. Anyway, so we want to indicate quantities that could be measured by the student that would allow them to determine UK using a graph. So I only have a meter stick. There are only two possible things that I could measure. So I could measure the compression distance of the spring. I could measure the distance that the block slides after it gets launched by the spring. Okay? That's it. The end. So for II, so that's part I, for II, we want to describe a method to reduce experimental uncertainty. So we're literally just going to say what we did before, maybe adding a little bit. So I'm going to squish spring. So I'm going to squish the block into the spring and measure that compression distance. So push block into spring. And then we're going to release and measure the distance that it slides. Now, the important part is the whole repeat for multiple trials part to reduce uncertainty. With the new exam redesign, you need to be specific about what you're changing every time in order to get that point. So we're going to push the block into the spring, measure the compression distance of the spring. We're going to release it, measure the distance the block slides after leaving spring, until it comes to rest. That's the important part, actually. And then we're going to do it again after changing the thing we have control over. So we have control over how far we push the block into the spring. So we're going to repeat for different compression lengths. That's it. The end. Short, sweet, to the point. You don't need to write a novel. You don't need to do that whole tell an alien how to make peanut butter and jelly sandwich thing that you did in elementary school 100 years ago. It's just, what are you going to do? What are you going to measure? What are you going to change? Repeat. The end. All right, so for part B, we want to indicate quantities that the student could graph on the horizontal and vertical axes to create a graph that could be used to determine UK. So we already said that we were going to measure the compression distance. So we're going to measure our compression distance. We already said we're going to measure the distance the block slides. So that better be in our answer for B. So that means we need to think about how those two things are going to be related. Now again, anytime you have a spring and then you're launching stuff off of your spring, 99% of the time it's going to be conservation of energy. So that's what we're going to do. Conservation of energy. So if I think about what's going on in this problem, let's draw a beautiful little bar chart. We compress our spring and we get a bunch of springy potential energy. Then we let our spring go. When we get back to x equals 0, the spring is at its relaxed length. So there is no springy potential energy. It has turned 100% into kinetic energy because there's no friction at this point. So there's nothing to steal it. Then we go slidey, 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 slidey. until eventually we come to rest. So we have nothing. Now, we go from U spring to K. There's 100% energy conservation there. Once we reach X equals 0, we start getting friction in this zone before we eventually come to rest. So I had a bunch of energy here. It needs to get sucked out via work in order to get us to come to rest. So that means friction does a bunch of work here. So we get some work done by friction. Okay. Now, I don't care about how fast the block is going at the end of this journey through the springy time. So I'm going to chop out that intermediate step and I'm going to do my conservation of energy this way. So I start with some spring potential energy, which goes like 1/2 K compression distance. What do we want to call that? I don't want to call it X because that's how we slide. Let's call it S. We're going to call you S. So 1/2 K S squared is my spring potential energy. Then I do a bunch of work done by friction. So work done by friction slurps it out of my system. And then I come to rest. There's no energy at the end. So there's my beautiful equation. So I'm just going to rearrange that. All right, so work done by friction. If you remember, work is force times displacement, or our fancy integral one, F dot dx. In this case, friction is constant, and it's parallel to our displacement, so we can use the good old force times distance. So over here, I'm going to get the force of friction times the distance that it slides. So since we start sliding at X equals 0, and we come to rest some position later, I'm going to call you X. So that's going to be the distance that my block slides. Okay. Now, force of friction goes like mu kinetic times the normal force, since we're sliding. And our normal force in this case, if we draw our little free body diagram, we've got the weight of our block, we have the normal force of our block, and then friction is going to be slowing us down. So our normal force is equal to our weight. So it's going to be mg. We get 1/2 ks squared on this side. All right, so now going into our whole linearization exercise. The two things I measure are S and X. So here's my S, here's my X. That means I have options of how I want to plot this. So option number 1, I could do it at face value. So I could plot 1/2 ks squared on the y-axis. I could plot, we're looking for mu at the end of the day, right? I could plot mgx on the x-axis, in which case that mu is going to be my slope directly. Now, I personally don't like plotting variables multiplied by known values on the axes. So what I personally would do is I would isolate one of these. So I would isolate s squared. So I'd multiply my 2 to the other side. So I'd get 2 mu k mg, and I'd divide by the spring constant k x. So then I have s squared versus x. So in that case, if I plotted s squared on the y-axis, and my slidey distance x on the x-axis, that slope would be all of this stuff in front. That's how I like to do it, just because I think it's cleaner to plot the actual data and then to analyze the slope from there. You could also take the square root, so you could also do s versus root x, in which case your slope would be the square root of that stuff, 2 mu k mg over k. You could switch your axes. So you could do x versus s squared and then multiply all that stuff to the other side. So it'd end up being the reciprocal. There's a lot of different ways you could do it that are totally valid. The important thing is that you have some quadraticness versus some linearness. So somebody's getting squared or rooted on your axes. All right, so then for II, so this answer, so for I, we would plot, for me, I would do s squared versus x. And then II, the slope would be 2 mu k mg over k. And it says that your answer may include an equation that relates mu k and the chosen feature of the graph. So this is fine. You don't have to do anything after that. You can stop there. Okay. All right, in part C, we have a totally new situation. This time we're smushing our spring and then we're launching the mass up a ramp and we're measuring how high does it go. So luckily for us, there is no friction this time, which means this is straight up conservation of energy again. We're starting with a bunch of springy potential energy. Yay. And 100% of that is turning into gravitational potential energy at the top. So our springy potential energy, 1/2 ks squared, turns into gravitational mgh. Okay? Now, here, that again tells me I'm looking at s squared and h. If you did not know how to get this relationship, use Desmos to kind of figure out what it's going to look like. So if you haven't looked at my how to scrape up points on FRQ 3 yet, link is in the description. Okay, so if we come over to Desmos, let's go ahead and put in the data exactly as they give us. So S was 0.02, 0.04, 0.06, 0.08, 0.1. My H's were 0.02 also, 0.04 also, 0.13, 0.18, and 0.33. Now, if I look at that, that looks kind of quadratic-y. Notice how it's like kind of curving up. That's my cue that I probably want to put x squared. Because quadratics go like s squared. So let's make x squared. Let's make an x squared table. So I'm going to take all the same y values. So we're going to take those x squared values and we're going to square them. So 0.004. So now if I look at my axes, that looks a lot better. So that tells me that I want to put x squared down here instead. So if I go back over to my graph, that was s squared. And then on our y-axis was our h. So that's what I'm going to plot. I'm going to do s squared versus h. So on my horizontal axis, I had s squared. That was measured in meters. So that's going to be meters squared. On my vertical axis, I'm going to have the height, and that was measured in meters also. So my h values were 0.02, 0.04, 0.13, 0.18, and 0.33. My s squared values were 0.0004, 0.0016, 0.0036, 0.0064, and 0.0100. All right. Now, I'm going to go plot those points just like we did on Desmos. The nice part about having this graph paper as opposed to the one in the released PDF is you have a lot more flexibility with how you're going to label your axes down here. So I'm just going to scooch this over so I can actually see it. That was meter squared. Label your axes because otherwise you'll lose some points. All right, we're going to label our axes. So H has to go between 0.02 and 0.33. All right, so it's 30 boxes tall. So just shy of what we need. So I'm going to go by, we'll say fives. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Great. So this is going to be, we'll say 0.1, 0.2, 0.3. 0.4. That's more than, a little bit more than half the graph. That's fine. All right, S squared has to effectively go between 4 and 100. So I'm gonna count by 20. So 1, 2, 3, 4, 5. So 20, 40, 60, 100. And that's gonna be 0.0, 0.00, 0.00, 0.00. All right, let's graph these bad boys. All right, we're gonna draw our line of best fit. Good enough. All right, so I got the same amount above and below, where there's an odd number of points, so maybe not. If you're gonna do this by hand, you wanna look for good places. So this looks nice. It's a nice intersection point, and ooh, you look nice. You look nice too. So those 2 points are gonna be 0.44 and 0.14 and 0.48. 0.116. 116. Oops, I forgot some zeros. My bad. Oopsies. 0.0044. 0.0044. Okay. And that was 0.3246. Yeah, 0.36. 36. All right, if we're going to find our slope, we do handy dandy y equals mx plus b. However, we're going to want to make sure that we're utilizing our equation to help us figure out what that slope is going to be. So we put s squared on our x-axis, which means I want to rearrange this so that it looks like y equals mx plus b. So h was on my y-axis, so I'm going to put mgh 1/2 ks squared. I'm going to isolate my h by dividing my mg over 2mg with a k and an s squared. So y x squared, so this is going to be my slope in this case. Okay, so let's figure out our slope. If you did your points by hand, we're just going to do good old y2 minus y1 equals x2 minus x1. Okay, so my slope is about 30.55. I'm going to set that equal to k over 2mg. So my spring constant, which is what I'm looking for, is going to be 2mg times my slope. They said the mass was 2 kilograms. I'm going to use g is 10 meters per second squared. My slope was 30.55. If you want the units of your slope, rise over run. My y coordinates were meters. My x coordinates were meters squared. So that's going to be 1 over meters for my slope. So I end up getting kilogram meters per second squared, which is a Newton per meter, which is what our spring constant should be. So if we punch that into our handy dandy calculator, we get about 1222 newtons per meter, approx. If you wanted to use Desmos to do your regression, you just need to specify that you used Desmos. If you don't tell us you use Desmos to find slope, then best fit line, then you're not getting that point. So if I do that on Desmos, we're going to say, hey Desmos, do y equals mx plus b using my y coordinates, which were h, which we named y2, and my x coordinate, which was s squared. So that slope is going to be 31.95 in that case. And if you do the exact same process, we're going to get 31.95 times g times the mass times 2. We're going to get 1278 in that case. So you're going to get a little bit of a range of answers. As long as they're in like the 12 to 1300 range, then you're good. Okay. The end. We finally did it. Yay.